Calculus is the branch of mathematics that helps us study change. It's like a powerful tool that helps us understand how things move, grow, and interact. Single variable calculus, which you might already know, deals with functions of one variable, like the height of a ball thrown vertically upwards as a function of time. But the world is rarely that simple. We often need to work with functions that depend on multiple variables. This is where multivariable calculus comes in. Multivariable calculus extends the ideas of single variable calculus to functions of multiple variables. Imagine you're trying to model the temperature in a room. The temperature might change depending on where you are in the room and at what time of day you measure it. To describe this, you need a function that takes in both your position in the room, which has 3 coordinates, x, y, and z, and the time t, as inputs. This is a function of 4 variables. Multivariable differential calculus helps us analyze how such multivariable functions change with respect to each of their input variables. It gives us tools to study rates of change, find maximum and minimum values, and much more. This branch of mathematics has applications in various fields, including physics, engineering, economics, and computer science. In this journey through multivariable differential calculus, we'll explore key concepts like partial differentiation, total differentials, Euler's theorem, and Lagrange multipliers. Understanding these tools will provide you with a solid foundation for tackling more complex problems and applications in various fields. One of the fundamental concepts in multivariable calculus is partial differentiation. It allows us to study how a function changes with respect to one variable while holding the others constant. Imagine you are standing on a hillside. If you walk north, you will experience a certain rate of change in elevation. If you walk east, you might experience a different rate of change. Partial derivatives capture these different rates of change. The partial derivative of a function with respect to a particular variable tells us how the function changes as we nudge that variable slightly, keeping all other variables fixed. For example, if we have a function fxy equals x squared plus 2xy plus y squared, the partial derivative of f with respect to x, denoted by fx, tells us how f changes as we slightly change x while keeping y constant. To calculate partial derivatives, we treat all other variables as constants and differentiate the function with respect to the variable of interest, as we usually do in single variable calculus. In our example, fx equals 2x plus 2y, treating y as a constant, and fy equals 2x plus 2y, treating x as a constant. In the previous section, we saw how partial derivatives help us understand the rate of change of a multivariable function with respect to one variable at a time. But what if we want to understand the overall change in the function as we change all the variables simultaneously? This is where the concept of the total differential comes in. The total differential of a function, denoted by df, combines the information from all the partial derivatives to give us an approximation of the overall change in the function. For a function of 2 variables, fxy, the total differential is given by df equals fx dx plus fy d. Here, dx and dy represent small changes in x and y, respectively. The total differential tells us that the overall change in AF is approximately the sum of the change in f due to the change in x plus the change in f due to the change in y. A related concept is that of an exact differential. An expression involving differentials, like df, is called an exact differential if it represents the total differential of some function. Checking for exactness is important in various applications, particularly in thermodynamics and physics.